lot of things are actually the theory portions. We'll discuss a theory in brief, and then we will move on to discussing some problems. So I've already shared a worksheet with the team, so you must have already got it. So once we're done with the theory, we will get back to it. We'll get back to the worksheet and solve. Those questions are from the previous year questions from HCU and few other Jamia Millia and few other universities, central universities. Right. So oscillations. Okay, so first of all, let's discuss about the equation of motion for the simple harmonic oscillations. So we are basically talking about simple harmonic motion. And the equation of motion can be derived quite easily using this expression. So we have from Newton's second law that F is equal to m into d square x by dt square. And obviously from Hooke's law, we have F is equal to minus kx. So if I combine them, I have the equation m into d square x by dt square is equal to minus kx, or which can be rewritten as d square x by dt square plus k by m into x is equal to 0. So this equation we are all familiar with. This is the typical equation of the simple harmonic oscillations. And very simply put, if we do a dimensional analysis, we know that k is equal to force constant and m is mass. Assuming that actually we have written this system by assuming a mass, by considering a mass spring system in which we have a spring and a mass attached to it. Okay. So considering this, this equation actually tells you about the restoring force, right? And m is the mass. So if I do a dimensional analysis, k by m happens to be we'll have the dimensions of square of frequency. So we set k by m to be equal to omega square. So we eventually write the equation as dx square by dt square plus omega square, which is equal to 0. That happens to be our second order differential equation, which describes an entire class of simple harmonic oscillations. Now, what are the solutions? So it's a second order differential equation, homogeneous second order differential equation. So a basic theory, I'm not getting into the details of the methods of solving that equation, but it's fairly understood that the solutions are in terms of harmonic functions. Like you can have solutions of the form of x of t is equal to like a cos omega t plus phi, or you can equally have y of x of t as a sine omega t plus phi. And from the theory of linear differential equation, a combination of these two can also be a solution, a source of a cos omega t plus phi plus a sine omega t plus phi. So a linear combination of these two solutions also can be a solution to that differential equation that we have written. So we'll take one of these equations, probably one or two. So we have three possible solutions. We can take any of these solutions. It's absolutely fine. So let's take the first equation and let's calculate. Let's find out what is the velocity. So this is the displacement. This is the equation for displacement. So most of these things, introductory stuff, are actually +2 level, but it will be quite easy for you. But still, it's always good to revisit them once. So velocity, u of t, can be calculated by differentiating x of t with respect to time. So if we differentiate cos, we get, am I right? Minus sign, right? Cos omega t, yeah. Now, if you want to find the acceleration, we again differentiate with respect to time. So we get dv by dt, sorry, yeah, which will be minus a cos, okay, I'll have an omega here. I'm sorry. Oh. So I'll have an omega here, and in this here I'll have a omega square. Okay, omega square a cos omega t plus phi. Right. Now this is the very important equation. This equation that I've written here. So this equation, so a cos omega t is nothing but x of t. Right. So this equation can be written as minus omega square x of t. Okay. So this is the most important equation, or this is something like a fingerprint of simple harmonic oscillation. So this is one equation that you can always check whether a given motion is simple harmonic or not. If the acceleration is given by something of this sort, or I can say that the acceleration is directly proportional to the displacement. So for any system, if the acceleration is found to be directly proportional to the displacement, then we definitely say that it's simple harmonic in nature. So normally it is said that this equation is the fingerprint of a simple harmonic oscillator. So very, very important equation this. Now let's do the energy calculations. Energy of a system. So let's calculate the kinetic energy first. So kinetic energy is half mv squared. So which is half m into minus a sine omega t plus phi, the whole square. So you get half m a squared sine square omega t plus phi. That's the kinetic energy. And potential energy is given by the formula half kx squared. I won't derive these equations. That's all. You can find it in the NCERT textbook or any basic physics textbook, something like H.C. Verma or Halliday, Resnick and Walker. I strongly suggest you to read H.C. Verma or Halliday, Resnick and Walker for a good grasp of the theory part of it. Half kx square is half into k a square cos square omega t plus phi. Right? So we got the expression for the kinetic and potential energy. Now we want to calculate the total mechanical energy. Total energy, which is equal to kinetic energy plus potential energy, which happens to be half m omega square, a square sine square omega t, plus half k a square cos square omega t plus phi. Okay, here also I have a phi. Okay, now m omega square is obviously k. That's what we have already used. We found out that k by m is equal to omega square. So m omega square is equal to k. If we substitute back here, we find that total energy is equal to half k. Now m omega square. This k a square becomes common in both the cases. In the bracket, you will have sine square omega t plus phi plus cos square omega t plus phi. So this is obviously 0. So we end up with the equation total energy is equal to half k a square. Right? Again, we know this. So total energy of a simple harmonic oscillator depends only on the amplitude and also on the force constant. But this is a constant anyway. But it doesn't depend upon anything else. As far as the qualitative features of the oscillation is concerned, it depends exclusively on the amplitude. Okay? Now a little analysis, because this is important, because from these equations that we have just discussed, questions used to come. Okay? So let's just briefly discuss what all things. What are all the variants of these equations? So we have the kinetic energy equation as half m omega square a square sin square omega t plus phi. Okay, and we have potential energy as half k a square cos square omega t plus phi. Okay. Now, if and x is given as a cos omega t plus phi. Now, if you look at carefully, this equation can be written as, see, just try to, so we know that a square cos square omega t plus phi plus a square sin square omega t plus phi should be equal to a square, right? Absolutely no question about that, because a square is the a common factor. So cos square plus sin square is 1. So you get a square. So a square sin square omega t plus phi can be written as a square minus a square cos square omega t plus phi. Okay? Now, a square cos a cos omega t is x, right? So we may write this as a square minus x square, right? So a square sin square omega t can be written as a square minus x square, which means that the kinetic energy equation may be rewritten as half m omega square into a square minus x square. Okay, this is a quite useful equation, which will come handy when you're trying to solve problems involving energy. Okay, I hope this is clear. Now let's see if this is okay, if this is correct. So this can be written as so let's add this with, so m omega square is k, so I get k into a square minus x square. Let's add it with the potential energy, which is half kx square. So basically you see that minus half kx square goes off and you are left with half ka square, which means that equation is fine. Okay, so this is another equation for the kinetic energy, which will be, as I said, which will become useful when we solve problems. Okay. Now, let's see. Okay, now the kinetic energy is half k a square minus x square, and potential energy is half k x square. Now let's check at what positions ke is equal to ke max. Now you see from this first equation that, okay, and total energy is obviously half k a square. And also the maximum possible energy in a simple harmonic oscillation setup is also half k square, right? It cannot go beyond this value because that's the total energy. So the maximum possible energy in an oscillatory system is half k square. Now let's check when is kinetic energy is equal to k max. So if you substitute x is equal to 0 in this expression, we find that kinetic energy is equal to half k a square. And obviously, where is x equal to 0? It is mean position. Okay. So at the mean position, the energy is purely kinetic, which means that the total energy would be still half k square, right? Okay, let's see at that position at x is equal to 0, what is the value of potential energy? So if you substitute x equal to 0 over here, we find that potential energy is equal to 0, which means that at mean position, ke is equal to ke max, which is equal to half k square, which happens to be the total energy, and potential energy is equal to 0, which means that we may rephrase this in the following way. The energy at the main position is purely kinetic. So that's one conclusion that we can have. Okay, so we say that at the mean position, kinetic energy is equal to its maximum value, which is also equal to the maximum value of the mechanical energy. So at the mean position, the total energy is purely kinetic. Now let's see at the amplitudes, that is at x equal to a. Let's see what is the value of kinetic energy. Obviously, x becomes a here. So a square minus a square, kinetic energy is 0. Right? So if I draw a curve where this is the x and here I have the energy value. Okay. So this is the amplitudes minus a and plus a, and this is the mean position x equal to 0. Right. So this is x equal to minus a and this is x equal to plus a. So if you look at the previous page, what we have found out is at the amplitudes, which is x equal to plus or minus a, at both the amplitudes, kinetic energy is 0. But at the main position, kinetic energy has its maximum value, which is half k square. So if I draw a curve, here it's 0. The kinetic energy is 0. And let's say this line over here is the total energy, which is half k square, maximum energy. Then at the main position, the kinetic energy will have its maximum value. So this is how the kinetic energy curve will look like. Right? Now, in the exactly similar way, if we analyze the potential energy, so in this curve, it's very clear. At the amplitudes, kinetic energy value is 0. So this is the x equal to 0 line. Sorry, y is equal to 0 line. So which is E is equal to 0, this line. E is equal to 0 over here. So at these two positions, total energy is equal to 0. Total kinetic energy is equal to 0. Sorry, yeah. Kinetic energy is 0 at these two positions. And at this position, it has its maximum value. Now also let me have, just for a reference. Now let's look at the potential energy function. It's half kx squared. Potential energy is equal to half kx squared. And it's very simple to see that when x equal to 0, potential energy is equal to 0. We have already seen that. Because if energy is purely kinetic, obviously it means that at some position, potential energy is equal to 0. Sorry. If at some position, energy is purely kinetic, it's absolutely sure that at that position, potential energy would be 0. Now at x is equal to plus or minus a, the potential energy will be equal to half k a square. You substitute x equal to minus a here, we get half k a square. If you substitute f is equal to plus a here, we get half k square once again, which means that at the amplitudes, potential energy is maximum. And at the main position, potential energy is minimum. So if you draw a curve, at these positions, we have the maximum value. And here we have it 0. So my curve will look like this. Okay, so this is the curve that represents energy of simple harmonic oscillator. Okay? So the green line corresponds to the potential energy and the red line corresponds to the kinetic energy. So, and this line over here, which I will draw in yellow, is the total mechanical energy, or which is nothing but the maximum possible energy, half k square. Right? Now, obviously, energy conservation principles works here because see, what basically happens is that at the main position, sorry, we'll qualitatively see it. At the main position, K is maximum. Now, as it goes towards the amplitude, the kinetic energy decreases. Kinetic energy decreases and potential energy increases. And by reaching the amplitude, what happens is that kinetic energy becomes 0 and the potential energy becomes half K square, obviously. So what's basically happening is that entire kinetic energy is being converted into the potential energy as it reaches the amplitude, right? Which means that energy is basically conserved. Obviously, for free oscillations. This is not applicable to damped oscillations, which we will see later. But right now we are discussing free oscillations. So for free oscillations, the energy is conserved. So if you think of a pendulum, this is the amplitude. Here potential energy is maximum. As it comes down, this particular potential energy will get converted into the kinetic energy, attaining its maximum value at the bottom. Okay. Attaining its maximum value at the bottom, which means that here the potential energy is half K square, and here the kinetic energy would be half K square. So here kinetic energy would be 0, and here potential energy is equal to 0, which means that whatever potential energy it had over here, which is half K square, had been converted into the kinetic energy over here. So you have a 100% energy conversion happening, which is one of the typical features of conserved systems. And we can always show that by using this expression for potential energy, that energy is conserved, right? By calculating from this expression, we can always find that by work done, by doing this integration f x1 to x2 f dx, this is the expression for the work done. And if I substitute f is equal to minus kx over here, perform this integration, and then I substitute the limits, x1 is equal to x2, I can always show that this integral goes to 0. Simple, which is actually a typical feature of conserved systems. Work done over a closed circle is always 0, right? So in this way also quantitatively we can prove it, but it's a time-consuming and useless exercise for the present purpose. So I'll not enter into the details, but it's quite easy to see it. So you can integrate this, and you can actually see that when in the final result, when you substitute x1 is equal to x2, the work done will go to 0. Okay, so quite easy to see that. Right. So that completes the basics of it. That's the that's the simple basic stuff that we have to discuss. Now let's see superposition of SHM. Okay, we got to see the superposition of SHM. So there are two types of superposition. One is two SHMs which are perpendicular to each other, and the other one is superpositions which are in the same dimension. So we will first see along the same line. Just a minute. Okay. Just to make sure that I hope you haven't asked anything. Okay. Fine, I'll continue. Right. So we'll just see how to find out. Okay, along the same line. Let's say we have two oscillators, and we should see. We are trying to see how the oscillation will look like when we combine them. When I say along the same line, which means that I have two oscillators, where x1t is written as a1 cos omega t plus phi. Okay. And x2t is equal to, one second, a2 cos omega t plus phi. So first case we are actually looking at same frequency. Both the oscillators have the same frequency. Give me a minute. Right, same frequency. And let's say its phase is phi1, its phase is phi2, okay? Phase constant, initial phase constant. We'll have a more general derivation, and from the results we can extract special cases in the end. Now let's see what is the resultant oscillation. X of t is equal to x1 of t plus x2 of t. Again, I'll not do the derivation in detail here. I've shared a material. Probably I will ask the Rashid. Are you there? Okay, it's okay. So I've shared a material which will be available to you through the drive. Okay, so in which the details of this derivation will be available. So I'll just go to the results directly. So finally, my results would be something like this. The resultant oscillation will be given by an equation like this: A cos, okay, omega t plus phi. Okay, so if you look at this, this is still an SHM, right? This is still an SHM because it's still in the same form as x1 or x2. But only thing is that A is different from A1 and A2. Phi is different from phi1 and phi2. Now, how to find A and phi? Now, A is given by the expression. Again, so A cos phi is given by the formula A1 cos phi1 plus A2 cos phi2. And A sin phi, actually that comes from, expanding this using cos A plus B. And then rearranging those two terms, actually we will get these forms. So A1 sin phi1 plus A2 sin phi2, right? This is what, this is from which this A comes in, okay? So A is something that depends upon phi1 and phi2 also, right? Now, there is another formula that will help us calculate A. So A is given by the formula, sorry. Again, the details of this derivation can also be given. I'm not doing the derivation here. I'll do the results. Plus 2A1 A2 cos phi1 minus phi2. And also phi can be calculated from the expression tan inverse of plus A2 sin phi2 whole divided by plus A2 cos phi2. Okay, so these are the expressions. So this is the resultant amplitude. And this is the resultant initial phase constant. Okay. This is the resultant amplitude. And for same frequency along the same line. And the resultant oscillation is given by the formula A cos omega t plus phi. If you see the resultant oscillation will happen with the same frequency as that of the original frequency, but the phase, we will have a modified phase and a modified amplitude, both of which are given by these two expressions. Okay. Now let's check some special cases. Case 1. Let's say there is a phase difference of, let's say phi1 minus phi2 is equal to 0. Okay, there is no phase difference. Then let's see what is amplitude. Then the resultant amplitude would be square root of A1 square plus A2 square plus. So this is 0. Cos 0 is 1. So you have 2 A1 A2. And that's nothing but A1 plus A2 the whole square root of, or which is equal to A1 plus A2. I hope this is clear, right? So this is a1 plus a2 the whole square. So we take a square root. So this is simply a1 plus a2. So if there is no phase difference, the amplitude of the resultant oscillation will be simply a1 plus a2. It's quite illuminating to see that if a1 plus a1 is equal to a2 is equal to a, then it becomes a is equal to 2a, right? The amplitude gets doubled. So simply amplitude gets added up. Now the other case, the next important case, case 2, let's say phi is equal to pi. Okay, let's say there is a phase difference of pi between them. Then the resultant amplitude would be, we have cos pi is equal to -1. Sorry, not phi, okay? Phi 1 minus phi 2. Phi 1 minus phi 2 is equal to pi. Then cos pi is equal to -1. Then the amplitude expression for the amplitude would be a1 square plus a2 square minus 2a1 a2. Because cos phi 1 minus phi 2 is -1. And eventually that will give us a1 minus a2. Okay. So, okay, this is the value if the phase difference is pi. Now let's take another case where phi 1 minus phi 2 is equal to pi by 2. Okay. Then cos pi by 2 is equal to 0. Then we have the expression a is equal to square root of a1 square plus a2 square. Okay. That's all. I don't think we can simplify this any further. So I think that's it. So these are the three special cases that we would look at. Okay. Now look at this expression over here, which tells you that if we have two oscillations, and if we combine them, if we have two oscillations with a phase difference of pi between them, and let's say their amplitudes are the same, okay, and then you directly see from here that the resultant amplitude is 0. So even though we have two oscillations, if the phase difference between them is pi, the amplitude gets cancelled, right? So that's something we should always keep in mind, we should remember. Now, I can compile this. I can have some more conclusions from it. So if I have two oscillations, so if you have any questions at this point, please go ahead. Okay. I'll just make sure that there is nothing in the chat box. Okay. No. Fine. Okay. Now, what I can conclude is that in summary, let's say we have same frequency and, okay, same frequency. The maximum amplitude would be a1 plus a2. Minimum amplitude would be something like a1 minus a2. And depending upon the phase difference between them. So you can have a maximum amplitude of a1 plus a2 and a minimum of a1 minus a2. Okay. So this is the conclusion that we can have. And even if a1 is equal to a2, we can also have 0 amplitude as a resultant. Okay. Now again, let's go to the superposition. But here the difference would be different frequencies. Different frequencies. So let's say we have x1, which is given by the formula a cos omega 1 into t, and we also assume that the initial phase is So x2 is equal to a cos omega 2 into t. Now, if I add them, we have x1 of t plus x2 of t. And for the convenience, I'm defining two frequencies here. One, let me call the modulating frequency, which let me write it as omega 1 minus omega 2 by 2. I'll tell you what are these. And then let me define an average frequency, which is of the form omega 1 plus omega 2 divided by 2. Give me a minute. Sorry, students, please. All right. So if I add these two, again, I'm not going into the details of the derivation. We get something like this. The resultant oscillation will be given by the formula 2a cos t into cos omega 1 plus omega 2 by 2 times t. So this is the expression for the resultant oscillation. Okay. So using these definitions, we can write this as 2a cos omega mod times t cos omega average times t. Okay, this is the expression for the resultant amplitude. Now, if I plot this, we have some interesting things happening over here. So you see, okay, I'll take a new page. So I have x of t written as 2a cos omega d into t cos omega average into t. Okay? This is the expression that we have. Now this is the amplitude. This term that we have is the new amplitude, or we call it the modulated amplitude. So if I call it something like a mod, this expression can be written as x of t is equal to a mod cos omega d into t. Okay. Now this is the resultant expression that I have. Now this pretty much looks like an SHM, right? Looks like an SHM. Because the equation of motion is pretty much like an SHM, because we write SHM usually as a cos omega t. But this is not an SHM. This is not an SHM precisely because the amplitude is now time dependent. Under this circumstance, we cannot guarantee that this would behave as a simple harmonic oscillator. You look at here, this is the amplitude. So this amplitude entire term actually depends upon the time. So it's time dependent one. And at best, we can also think of it as periodic. But again, periodicity also cannot be guaranteed generally. But probably it's better to describe it as periodic, but not as simple harmonic. So this is something typical feature of addition of two simple harmonic oscillators with different frequencies. It will not be an SHM in general, but it can be periodic. Now, if I plot them, this you can also plot by using some graphing softwares as simple as you have Desmos. Just try to plot it, plot that function. You will see something like this. So you will have, okay, one more thing that I want to specify here is, see, omega average is, okay, I'll write it in the next page. So we have two frequencies over here. One is the W mode, which is defined as W1 minus W2 divided by 2. And I have another one, W average, which is equal to W1 plus W2 divided by 2. Now, if you look at them carefully, you obviously know that W average is much greater than W mode. Right? This represents a slow variation, and this represents a fast oscillation. Slow oscillation and a fast oscillation, right? So you are combining actually, now in this expression, you're actually multiplying a fast oscillation with a slow oscillation. And the result would be very interesting, something like this. So you'll have a sine function behaving like this inside. So the amplitude will go down like this. Again, the amplitude will pick up like this. Sorry, I'm very bad at drawing on this. Now, this is the this thing, omega 1 plus omega 2 divided by 2. Now, this thing that you see here, the modulating frequency will go like this. So you see an envelope, right? Envelope. So this is how it looks like. Okay. So this is where you have the time axis. This is where the displacement is. So this is how the graph would look like. So this is SHM, two different frequencies. Now, if you think of it as a sound wave, you know, the sound goes up, decreases. So you say that you see a waxing and waning of sound. So something like, you know, you hear something like wow, wow, wow kind of a thing. So that's what we call beats in general, beats. Okay. So loosely speaking, you will have beats happening here. Now for beats itself, we have another condition to satisfy that we will see. We'll go to that. But right now, this is what will happen. Okay. Now, this thing over here represents one beat. This is another one. So you have a number of beats happening. And you have one maxima followed by a minima, one maxima followed by a minima. That's what is generally called as a beat. Okay. So in conclusion, if I have two oscillations with two different frequencies, but with the same amplitude, okay. If I generalize to two different amplitudes, we will see how to write the equations later on. If you add two different displacements, two different SHMs with two different frequencies, this is the resultant oscillation equation. So you have one part which is showing a slow variation, which is this, and another part which indicates a fast variation. So you're multiplying a slow variation with a fast variation. So you get something like this. And this is the final expression that we have. So we see that the amplitude itself is modulated by the frequency difference between them. Okay, right. And this is the expression that we have. And if I plot the displacements, okay, where is it? Yeah, if I plot the displacements, this is how it will look like. So you see, the faster oscillations will be modulated by the slower oscillations. So this is how it will look like. Okay, right. So you hear something like, you know, waxing and waning of sound. If you think of it as a sound wave, something like that. For example, like if you think of two tuning forks vibrating with different frequencies, you can always hear the difference. I'll give you a link which actually displays, which is actually a demonstration of beats. Right. Now let's see some special cases. Not some special cases actually. Let's say both of them are of different frequencies. Sorry, different amplitudes. So earlier we saw same amplitude but different frequency. Here we generalize it into different amplitudes as well. And if they are different amplitudes, then this A mode is given by the expression A1 square plus A2 square plus 2A1 A2 cos whole raised to 1. Okay, this will be the expression for the resultant amplitude, and the resultant phase. See, because of the difference in amplitude, a new phase constant also will appear. In this expression, if you see, the phase constant was 0. There was no phase constant. But if the amplitudes are different, a new phase constant also will reappear. And that will be given by the expression A1 minus A2 sine omega mod times t whole divided by A1 plus A2 cos omega mod into t. Now it's very easy to sort of see that if they are of same amplitude, let's say A1 is equal to A2, then the entire expression theta mod goes to 0, right? As in the case of previous expression. Okay, so if there are different amplitudes, our equation for oscillation would be something like this: A mod cos omega average t plus theta mod. Okay, if there are different amplitudes, same amplitude, the equation would be x is equal to A mod cos omega average into t. That's all. No theta mod. Okay. So you can always see that if A1 is equal to A2, this expression will go back to the earlier expression. Okay. So these are the expressions that we have. Okay. Any questions right now?
Sir, theta എന്ന് പറഞ്ഞ phase difference ആണ്. Phase ആണ്.
Phase difference അല്ല, initial phase constant. അതായത് phase constant. Phase constant. Phase difference അല്ല. Like if you plot, it will not start from the 0. Okay. If you start something like this, it's 0, right? Initial phase is 0. But if initial phase is not 0, it will be something like this. It will start much earlier than that, or it could even be. It can. How can I show it? Probably something like this. Yeah. Okay. If A cos 0 is equal to 1, something like this. It will not start from 1 probably. Okay. It's not. Sorry. A cos 0 is equal to 0. It should start from A. But if it has some phase value, it will start somewhere here. Okay. It goes something like this. Okay, I'll show it. I'll show both the figures. Okay, so in the first case, if they are of same amplitudes, it can look like this. So let's say this is one of the combining oscillations, A1. The resultant amplitude can also start from the same. Okay, it can also have the same, probably something like. It can also start from the same position. But if the amplitudes are different, the starting point would be different. It's probably somewhere like this. This would be the resultant amplitude. Okay, something like that. So the initial phase or the phase constant would be slightly different from that of the original waves that are sort of superposing. Okay, I think that's fine.
Okay, sir.
Right, now going ahead, let's briefly see what are beats. Now for beats, there is a condition that omega 1 should be as close to omega 2. Then in that case, we will definitely see beats. Okay, beats. Now look at this expression once again. Look at this expression here. So A mod is equal to A1 square plus A2 square plus okay, one second. I'll get back to this once again. I think I should explain it a little more clearly. So initial phase always means that it starts somewhere, right? It starts somewhere. So probably, let's say this is where A1 starts and X1 starts, and let's say this is where X2 starts. Okay, and this is A. Let's say this is minus A. Okay, and I have a green one which starts from here. Let's say it goes like this, blue one. Because its phase is written as cos omega t plus phi. So the argument of this will be always less than A. So it will start somewhere right here. Now this is x1. Now x2 will be A cos omega 2t plus phi. Right? So this should start from somewhere here. Maybe, I don't know, probably somewhere here, something like this. This could go something like this, and this could go something like this. Okay. Now, if they are of same amplitudes, wait, where is it? Where is it? Okay, it can, and if they are of different amplitudes, okay, if they are of same amplitude, you see that theta is equal to 0, which means that the resultant amplitude would be here. It should start from here. It should go something like this. That's the meaning. Okay, and if they are of different amplitudes, then it can also start from somewhere else. It will not start from the same amplitude. It can start anywhere else, depending upon A1 and A2. Okay, that's the meaning of it. Right. Okay. So you have 2A1, A2 cos 2 omega mod t whole raised to 1 by 2. This is the expression for the modulated amplitude. Okay. Now, what is it I want to tell you is that, now let's see the times at which A mod is maximum. Now, obviously, this equation, A mod is maximum when 2 omega dt is equal to 0, 2 pi, 4 pi, etc. Right? because that was the times when the value of this cos 2 omega dt is equal to 1. For odd multiples of pi, that would be equal to minus, and you will have the minimum amplitude. Okay, which means that at times 2 omega d or 2 pi by 2 omega d, etc., we will have the maximum amplitude. Okay, or which is to say that at t is equal to 0 by 2 into omega 1 minus omega 2, 0 by omega 1 minus omega 2, sorry, not 0, what is it, 0 and correctly. Oh yeah. Okay, that's the initial value that I don't have to consider. Here it should be pi. So t is equal to 0, pi by 2 into omega 1 minus, okay, pi by not 2. This 2 will get cancelled. No, you will have it 2 there. Okay, I'll write in different page. So at times 0 to pi by 2 omega d and 4 pi by 2 omega d, etc., or which can be written as 0, 2 pi by omega 1 minus omega 2, and here also I'll have 2 there, so 4 pi by omega 1 minus omega 2, etc., and which can be written as 0, 1 by mu 1 minus mu 2, 2 by mu 1 minus mu 2, etc. Okay, do you follow? Because mu is 2 pi omega is equal to 2 pi mu. So mu is equal to 2 pi by omega. So you can always write this equation in terms of nu. So I can write it as, so these are the times at which you have the maximas occurring. Okay, at t is equal to 0, 1 by nu 1 minus nu 2, 2 by nu 1 minus nu 2, etc. Now, if we check at what are the times at which A mod is minimum, that's when 2 omega dt cos 2 omega dt is equal to minus 1, and that's when 2 omega dt is equal to pi, 3 pi, etc. Okay, from which we can actually found out that the times are pi by 2 omega d, 3 pi by 2 omega d, etc. Okay, so these are the times at which omega mod is minimum. Okay. Now, if you, so your first maximum.
Sir.
Yeah.
What will be the time difference between a subsequent maxima or minima?
That's what we're going to calculate. You'll see that.
Okay, sir. Okay.
So for maximum, first maximum, let's look at the first maximum, or probably a maximum. Look at this here. Look at here. So let's take this value over here. So we have maximum occurring at 1 by nu 1 minus nu 2. Okay, now how can I write this equation? Rewrite this equation as first equation. Let's write this pi by omega 1 minus omega 2. This can be written as 2 pi by nu 1 minus nu 2. Wait, just a minute. Okay, where is it? Oh, no, wait. Mistake. Okay. Now this becomes 2 divided by nu 1 minus nu 2. Am I right? Just a second. So we have so 2 wait. Right. So what is it? Yeah, this is one maximum at 0. Okay, maximum occur here. 1 second. Give me a minute. Okay, you have one at 0. You have a maximum. Then you have a minimum at. Yeah, correct. Okay. So first maximum is at 0. Right? First maximum is at 0. Okay, I think I've drawn that figure a little wrongly. This figure is actually wrong for. It should be something like. Okay, it should be like this. It's basically cos, right? Both of them are cos. So it will not come like this. So I made a mistake over there. So this is basically sine. So this should look like this. Both of them are cos. So it should start from the other way around, right? So it should be like this. Yeah. And then it goes up again. Yeah. Okay. I hope you understood the mistake that I made. And it goes like this. Right? Yeah, this is how it should look like, because you look at this expression, both of them are cos. So it should be cos curve. I've drawn sine curve earlier. So it should be cos curves. So you see, at t is equal to 0, we have a maximum. And here we have a minimum. Again, we have a maximum here, we have a minimum, right? So that's what we see from the calculations as well. At t is equal to 0, we have the first maximum occurring at t is equal to 0. This is the first maximum occurring. And the first minimum will occur at a time. Okay, this is the first maximum occurring. And okay, I'll run talk. First minimum will occur at this time, pi by 2 omega d, which can be written as pi by 2 into omega 1 minus omega 2, which is nothing but 1 by mu 1 minus mu 2. Is that clear? Okay, this is wrong. This is okay? I mean, do you understand? Here. Is it fine here? Ask me if you have a question here. This pi by 2 omega d, I'm writing it as 1 by v1 minus v2. 1 by mu1 minus mu 2. Is it okay? Right. Since
omega d equals omega 1 minus omega 2 by 2, isn't it?
yes.
So 2 omega d equals omega 1 minus omega 2.
What?
Sir, pi by 2 omega d equals pi by omega 1 minus omega 2.
Yeah, correct. No, pi by 2 omega d is. This is correct, right? This equation. Oh, okay. You are saying that this 2 wouldn't be here, right? You will have a 2 here as well, right?
Yes, sir. Yes, sir.
Okay, right, thank you. So you have pi by omega d, right? But then I think I'm making a mistake somewhere. Pi. Pi by 2 omega d. What is that mistake I'm making? Okay, wait. Let me go about from the beginning. Okay, so this would be phi by 2 into omega 1 minus omega 2. Okay, which is okay. So f is equal to omega by 2 pi. Okay, I think I made a mistake somewhere. Are you able to identify the mistake anywhere? 2 omega t. What is my expression? Okay, we'll see. What my conclusion is that I think I have made some. I'm not wasting time over that. Now the time difference between, I'll clarify it. Okay, this confusion I'll clarify. Probably I'll write to you. Okay, I'll write the derivation and send it to you. I'm making a small mistake somewhere, but the time difference between, yeah, it's correct actually. Yeah, it should be correct. So this should be 2 by nu1 minus nu2. Is it clear? Right? It's okay. Yeah, it's correct now. 2 by nu1 minus nu2. I think it's coming out like this. Okay, maybe I'll do that later. I'll make a clarification later on. But I'll conclude what I want to say. Now the time difference between two maxima will be 1 by nu1 minus nu2. Okay, I'll derive it later. I'll tell you. Maybe in the next class we'll discuss how this comes. I'm making a small mistake around here. We can, but always find it, not a problem. Now here, this is the time difference between two maxima, which means that going back to the curve here, the time difference between this peak and this peak, this will be 1 by nu1 minus nu2. Okay, that's what we are all about. So, which means that the frequency with which the frequency of beats is actually 1 by t, which is equal to nu1 minus nu2. Okay, so this is the conclusion that we have. So the beats would happen at a frequency which is equal to nu1 minus nu2. Okay, that's the conclusion. Or I can always say that this happens at the angular frequency omega 1 minus omega 2. Now see, I can show it from the graph itself. Okay, where is the other expression? See, the entire oscillation happens with a frequency of, this red line, the frequency of this red line is W1 minus W2 divided by 2, right? The frequency of the red line, which is equal to W1 minus W by 2. But the frequency of the beat is W1 minus W2, which is actually twice of the frequency of this, which actually is visible in this. See, look at here. When one sine curve is completed, okay, let's start from here or something. Sorry, when one cosine curve is completed, when will that be completed here? It starts from here and it goes back here, right? This is one cosine curve. I'll draw it in green or something. So it's okay, green is green. So when one cosine curve is completed here, you see how many beats are happening? 2 beats. So within one cosine curve, we have 2 beats. I think it's visible. You have a half here, you have a half here. If I draw it further, it will be visible, and one full beat over here. So within one cosine curve, you can see 2 beats happening, right? So that's what we have discussed here as well. Okay. So the beats happens with a frequency equal to mu1 minus mu2, which is actually twice of the frequency with which the amplitude itself is changing, right? So this is what happens when we have oscillations superpose each other with 2 different frequencies. Okay. So you have a modulated thing happening. So you have, this is the equation governing the amplitude of the resultant oscillation, and you have a new phase constant arriving. So sorry, this is the expression. Yeah, you have a new phase constant appearing because of the difference in amplitudes. And if there is no difference in amplitude, there is no phase constant. Its initial phase constant of the resultant oscillation would be 0, and the resultant oscillation will look like this. So you have the faster oscillation, which is modulated by a slower oscillation. Okay? This is how it works. It's already 9:20, so probably we'll solve a few problems before we. I wanted to cover Lissaj's figures as well, but it's okay. We'll do it a little later. So I'll quit the board now, and I'll start a PPT. Give me a minute. I think I have a question. Abhirami R. Sharma, so like sine wave and cosine wave, can you explain that question? Abhirami, can you, if you can hear me? Yeah, actually, I have drawn, because our resultant oscillations were actually cos. The amplitude was also a cos wave, and the displacement itself was a cosine wave. But by mistake, I've drawn the sine wave. Both of them were sine waves. But in fact, I should have drawn both of them are as cosine waves. Okay. Yeah. You can take your worksheets. Probably, I think we can work out first few problems. Okay, I'll okay, is it visible? Is the PowerPoint visible? Please tell me if it's not.
It is visible, sir.
Okay, thank you very much. Right, so this is a Hyderabad University question, 2011. Okay, sorry. Okay. So look at this question. Consider a body. So this is asked in Hyderabad 2011. Okay. So consider a body of mass 500 gram connected to two springs as shown in the figure below. The springs are of equal length and spring constant. The body is displaced vertically upward by a small distance x and then left. Which of the following statements is true about the oscillations executed by the body? Option A, motion is simple harmonic and periodic. Option B, motion is simple harmonic but not periodic. Option C, motion is not simple harmonic but periodic. Motion is neither simple harmonic nor periodic. Now let's try to understand this problem. Okay, so I'll draw the system here. So if you look at this question, probably this is probably at a IIT JEE level, probably, right? IIT JEE, you get a lot of questions like this, JEE or NET, whatever you think of. Okay, so working out a few questions from a NEET book or JEE exercises will help you. You will see a lot of such questions in Hyderabad University questions, and in other, even I've seen it in Jamias also. Now this particular thing is displaced upwards, so I'll draw the upward figure also. Okay, so yeah, I'll draw it here. So this is how you displace it, right? This is how we displace it, and this distance is basically x. And let's say the length of the spring is L. Yeah.
I can't visible what you write, sir.
What I'm drawing, it's not visible to you?
No, sir.
Sir, you're presenting only the first slide.
Oh, actually, I've went to the next slide. It's not. Wait. You're seeing only the oscillations, the title one?
Yes.
Yes, sir.
Let's share it again. No? Do you see it?
Yes, sir.
Do you see the problem?
Yes, we can see.
Okay. So consider a body of mass 500 gram connected to two springs as shown in the figure below. The springs are of equal length and of same spring constant. The body is displaced vertically upwards by a small distance x and then left. Which of the following statement is true about the oscillations executed by the body? Okay. Yeah. So this is the original system. Now you're displacing it upwards, which means that you will displace it upwards like this. Okay, this is how it will look like now. Now this distance is x. And let's say the length of the spring is L. Okay, now this is how it works. Now we have to check, if you leave it, what kind of motion that would be. Okay, it's okay. I didn't. Okay, wait. Yeah. So basically, if you leave it, it's going to vibrate up and down. The question is whether it will be periodic, whether it will be simple harmonic in nature, or whatever it is. Okay, that's the question. So let's check it out. Now, to check it out, let's analyze what are the forces acting on it. Obviously, some tension will develop in the spring. So I'll remove the spring and I'll draw only the forces acting on it. So you have the tension which is developed in the spring along these directions, right? T and T. Now, if this angle is taken as theta, you have 2t cos theta here. Sorry, you have t cos theta here and t cos theta here. Okay, and here you will have both the sine components added together. 2t sin theta. Any question here? Is it okay? Do you follow? Yeah. Now, look at this. Now, the total restoring force in the spring would be 2t sin theta. Is that okay? Total restoring force with the spring constant, probably. So we'll avoid the spring constant and we'll see that the total restoring force will be proportional to 2t sin theta, or it will be equal to the sum of the restoring force of this spring would be along this direction, and this tension is nothing but the restoring force. So this is the another restoring force. So the total restoring force would be 2t sin theta. Okay. For the time being, I'm not involved in spring constants. I'll just see how it depends upon. I have other purposes. So I'll just see what is the restoring force. Now I can write this as m into d square x by dt square, which is equal to 2t sin theta, along with some constants, of course, which will be a resultant spring constant of these two, which doesn't really matter actually. So see, you have an acceleration here. Now from the diagram here, this is theta, this is x, this is L. So sin theta is nothing but x by L. So we arrive at a conclusion that d square x by dt square is equal to 2t by m into x by L. Now you see that acceleration is directly proportional to x. And we know that if acceleration is directly proportional to the displacement, it's a typical nature of simple harmonic oscillation. And if it is simple harmonic, it's going to be periodic as well, which means that answer A is the correct answer. Okay? So it's going to be simple harmonic as well as periodic. Okay. So I told you in the beginning itself that this nature of acceleration being proportional to the displacement is a typical feature of simple harmonic. So in many of the problems, you just have to check if the acceleration is proportional to simple harmonic. So you can have questions like you have something object which is placed on the surface of the water. Now, if you push the object into the water, what happens? The object will execute oscillations. Now, the question will be, will that oscillation be simple harmonic or not? Such questions can also come. You can see a lot of such questions in a NEET or JEE problem, NEET or JEE book. So for oscillations, at that sort of an exercise will help you a lot. Okay? Now look at one more question. This has a figure we haven't discussed, so we'll discuss later. Now look at this question. This will be the last question for the day, and then we will meet on the 13th. Okay. So we have a block of mass m rest on a frictionless horizontal table and is connected to two fixed posts by springs having spring constants K and 2K. If the block is displaced from its equilibrium position, the angular frequency of vibrations is given by C, again from HU 2012. So let's draw this figure first. Okay, so you have a mass M. This has a spring constant K, and this has a spring constant 2K, and it is supported by two fixed posts. Okay? Now you actually displace it from the equilibrium position, maybe towards this direction. Now let's see, if you look at this spring, I call it spring 1 and spring 2. If you look at spring 1, a restoring force will be developed towards this direction. Is that clear? Right? This is being compressed towards right, so a restoring force will be developed towards the left. So we have a restoring force which is equal to minus 2kx towards left. Right? Now if you look at this spring, spring 2, this will be elongated, which means that a restoring force will be developed in this spring towards left once again. So that F rest would be minus kx towards left once again. Is it clear to you all? I hope it's clear to you. So this is being compressed towards right, so a restoring force will be developed towards the left. Now this is being elongated towards the right, so a restoring force will be developed towards the left. Now the total restoring force would be minus 3kx. Absolutely no question about that, because basically these two are vectors, and we have two vectors acting in the same direction. So the resultant would be just the sum of those two, right? Now, you know what is the total force now? Now, from the total force, we can always find out the amplitude. So, wait, where is it? Now, this tells me that effective spring constant is actually minus 3k, right? Effective spring constant is minus 3k. Because F rest, the total restoring force, can be written as Ke, okay, Ke times x. So we have the equation minus Ke times x equal to. So this equation is the equation for both the spring combined system, where K is the effective spring constant. Now, if you compare these two, I can arrive at the conclusion that Ke is equal to 3k. Now we have m omega square is equal to Ke, which is equal to 3k. No, I don't have to write this minus here because we have minus on both the sides. So m omega square is equal to 3k, or omega square is equal to 3k by m. Okay, so that's it. So the angular frequency omega will be equal to square root of 3k by m. So answer would be A. Okay, so it's already 9:35. I'll stop here. Rest of the questions we'll try. Rest of the theory and questions we'll try later. Okay, I think that's all for the day. If you have any questions or any clarifications required, you can let me know. Any questions? Or if there are no questions, let's leave. Let's part ways for the day, and we'll meet on 13th. Okay, thank you guys. Yeah, thank you, Reena. Thank you, Abrami. Yeah. Rashid, are you still there?